I hit my 15-minute mark on part one. All right, gotta hurry up. So I think it cut me off, but I was saying just the big idea here is that we're understanding that we still have the law of conservation of mass. We still have the law of conservation of energy, although we are transferring energy and mass in that we're moving electrons, and it requires energy to move them, whether we're taking or giving them. We are always going to maintain that there is a conservation of energy and mass, so we're not losing anything. All right, let's keep moving here. So on the second page, the salt on your kitchen table does not spontaneously combust into flames. Why? The formation of a salt has an overall lower energy level than its substituent ions. So what we're thinking about when we have a ionic compound, when we have some salt in front of us, like the table salt in your kitchens, is that the chemical reaction has already happened. The forming of this ionic compound has brought this ionic substance to such a low energy level that it's going to remain at that energy level. So when we think about pure sodium or pure chlorine, that elemental sodium, that alkali metal, is very reactive. It's not going to persist in its elemental form. It wants to react. So too with chlorine. Now, chlorine can have an elemental form. It can react with themselves. That's one of the properties of our halogens. But when it reacts with sodium, it's a very violent reaction. It produces a lot of heat and light. Maybe I'll post a video of it too. But when you form the product, that product is really, really stable. So that is why the salt that is sitting in your kitchen table, it just sits there. It doesn't do anything else. It's not going to spontaneously have some chemical change. It's already at its lowest energy level. So when we talk about energy level, and all life for that matter, we say that the world wants to do the easiest thing possible, the thing that requires the least amount of energy. So when we're talking about energy, when we reference our lattice energy or things like that, it's all going to be what is the easiest thing? What is the thing that will happen that requires the least amount of energy? So moving right along here, we've got our next blank, lattice energy. So lattice energy, we can fill this in. The energy released when ionic bonds are formed. What is lattice energy? Lattice energy is the energy released when ionic bonds are formed. The lattice energy can be different for all different salts. So depending on maybe like the size of the atom, it might release more or less energy as they come together. All you guys need to know is that in forming a salt, in forming a ionic compound, that is more favorable. So these two cations, this cation and this anion, they want to be at their lowest energy state. So they're absolutely going to form a neutral ionic compound. They're going to form a ionic substance, and the ionic substance is going to have some properties that we'll talk about in just a second. All right, so when a salt forms, it is neutral overall, but its two atoms yield a separation of charge. So we're always going to have that cation part and that anion part. I really like the image here that is in your guided notes, and it's nice that it's actually color-coded because otherwise it would usually be black and white when I hand this out in class. But you'll notice we have this grid-like structure, so that is going to refer to our crystal lattice. You can also see these large atoms, these plus and minus atoms. Now, what I like about these atoms is they show how close they are to each other. So we can kind of see the electron cloud of our cation and our anion. And if we take a look, we have an alternation of charge. So if you have cation anion, they need to arrange themselves where the positive cation is completely surrounded in all three directions by some anion. It could not be that you have two cations next to each other or two anions next to each other, because that's like two negative or two positive ends of a magnet near each other. They're going to buff against each other. Versus if you have the opposite charge, positive, negative, you get that strong attraction. That's why we're going to talk about how ionic bonds have these really predictable properties, and they're all based on these charged attractions. So, all right. So we gave our lattice energy. Let's fill in these next couple blanks. Based on our electronegativity trend, the metal atom will always be blank electronegative, while the non-metal is always blank electronegative. Your electronegativity trend, just a reminder, points up towards fluorine. Our noble gases are not involved. So if we are talking about the most electronegative things like fluorine, halogens. So our halogens, our nonmetals, are going to be more electronegative, where our metals are less. Let's make sure we put it in order so you guys take it down in order. Metal atoms will be less electronegative. A non-metal atom is more electronegative. So again, a metal atom is less electronegative. Those are things like our alkali metals. They are less electronegative. They're not going to pull electrons towards it. In fact, they want to give them up. Versus our halogens, those are our classic nonmetals. They definitely want to gain an electron, pull it towards it. They have really high electronegativities, like fluorine. We talked about how fluorine is the powerhouse of electronegativity. It is also a nonmetal, so that's why, again, nonmetals have more electronegativity. All right, so I did talk a little bit about the crystal lattice image that we get here. Let's get our definition for it. What is a crystal lattice? A crystal lattice is the simple or regular pattern in which the crystal structure is arranged. Crystal lattice, what is a crystal lattice? A simple or regular pattern in which the crystal structure is arranged. So this could be something that you could do today if you want to go and play around with some salt in your kitchen, but maybe only if you have the really chunky sea salt. It's harder to see in like a baking salt, which is really finely ground. But if you look at salt, you'll notice it has these regular crystal structures to it. They're square. They're maybe even cube shape, you could say. So the reason why they have these really prominent geometries to them, they're not just like a blob or like a droplet, this amorphous kind of shape, is because of the alternation of charge. So on the molecular level, there has to be a cation and an anion next to each other. And because this is a repeating pattern over and over and over again, in the macro lens, kind of what we see with our eyes, we see this repeating geometric structure that we're calling a crystal lattice. So the smallest repeating unit in a crystal lattice, this is our unit cell. So the last blank before we get to properties, this is our unit cell. The unit cell is also kind of going to be what we refer to as like our formula unit. So that's like saying, oh, I have a sample of sodium chloride, NaCl, but NaCl is the repeating pattern, the unit, the molecule that stands next to each other over and over and over again, billions of times, so that we can get this physical substance in front of us. Again, reminding ourselves that atoms, whether they participate in ionic compounds or not, are exceptionally small. So in any sample, even a grain of salt, you have millions and millions of atoms in that sample. So when we say NaCl, although we might talk about like one molecule, one sample of that would have tons and tons and tons of those molecules in it. All right, so time to get to properties and to correct myself about using the term molecules. So lastly, we have properties, and then we'll be able to wrap it up here. So for properties, these are properties that I do expect you to memorize. We'll have properties for ionic compounds, and we will be comparing them to covalent compounds as we keep going. So it is important to know these properties. First and foremost, ionic compounds are not molecules. What? I've just been calling them molecules for the last, 18 minutes or so. So here's the issue. Ionic compounds, the force of attraction that holds them together, it's an electrostatic attraction. It's that magnetic positive, negative attraction. It's not a true bond. When we keep going into covalent bonds, and maybe you remember covalent bonds from middle school or last year in bio, but when we were talking about covalent bonds, this is when electrons are shared. In ionic bonds, it's specific because electrons are going to be ripped away and transferred fully from cation to anion. So just because of some of the definitions that we have seen and that we will keep seeing, ionic compounds technically are not molecules because they're just forces of attraction. They don't actually have a real bond. However, other chemists, other teachers, online resources, even your textbook will incorrectly call ionic compounds ionic molecules or just general molecules. So I want us to be able to understand that, yes, we do have some strict definition for what is a molecule, but we'll not take it too seriously here. We will refer to ionic bonds as a molecule from time to time. All right, so as we go through these, I'm going to say a little bit about each property, and hopefully I don't steal too much of your time and we can get out of here. All right, first and foremost, ionic bonds are strong. Ionic bonds are strong. The crystal lattice amplifies the strength of these bonds together. So we have a full positive, a full negative. They are pulling towards each other. They have a strong force of attraction, just like two ends of a magnet. However, this isn't just one cation and one anion. I'm going to scroll up to this image. Maybe we can take a look at it. In this 3D structure of a crystal lattice, what we understand is that in the center of it, so not those outermost edges, but in the center of this 3D structure, we will have some cation or some anion that is completely surrounded in all directions. So we'll have some negative or positive particle that, to sort of, I should say, in front, behind, to the left, to the right, on top of and below, in all directions, it will have an oppositely charged ion. So this means that not only does it have a strong force of attraction next to it, it has a strong force of attraction in all directions. So that's what I mean when I say the crystal lattice amplifies the strength of keeping these atoms together, because that formula unit, that unit cell is repeating over and over again, and we have a 3D structure of these positive, negative, positive, negative. It makes it really, really strong. So that's why we say ionic bonds are strong. All right, our next bullet point, their strong crystal lattice means they have high melting points and boiling points. Strong crystal lattice means they have high melting points and high boiling points. So a high melting point or boiling point for your salt means that's why you can just keep it on the shelf in your kitchen. There's no worry that on a hot day in the summer, the temperature is going to get up there and your salt is going to start melting. Versus, maybe you guys notice this with your sugar. So sugar does do this. Not that sugar melts all the way, but when it gets nice and warm out, sugar pulls a lot of water into it. So you'll notice like you'll get those chunks of sugar crystals in your bag of sugar, or if you have brown sugar, you will definitely notice brown sugar get moist and it'll get really hard, and it won't be like soft texture to it. So when we are thinking about ionic compounds and we talk about them having high melting points and boiling points, this is why they're always going to be solid. That will be our next blank. But we'll talk about how ionic compounds, you need a wicked, wicked, wicked high temperature to melt them. Another example might be if you are making baked potatoes or French fries, you can put salt on your potatoes, put them in the oven. You can crank that oven up to, 450 degrees Fahrenheit, and the salt is still on there. It's not like the salt melts or anything at that temperature. So you need incredibly high heats. At this point, I usually point over to Mrs. Stan's room. So in Mrs. Stan's room, she has a kiln. That kiln gets up to 2,000 degrees. That would be hot enough. I think for sodium chloride table salt, you need about 1,800 degrees Fahrenheit to melt it. That's just off the top of my head, just my memory. I think that's what it is, though. So you need incredibly high temperatures. This would be a temperature that would be way too hot to get in any oven or microwave. You would have to have something like a kiln to be able to get that kind of temperature. All right, so our next blank, I already said it, but this is why ionic compounds are always solid at room temperature. So always solid at room temperature. Again, every substance can undergo phase changes, so ionic compounds can absolutely become liquids and gases. It's just they would be incredibly hot. So when we think about, gaseous ionic compounds, that's like in the center of the sun. That's where gaseous ionic compounds are. It would have to be incredibly hot. It's not going to ever happen at our normal atmospheric conditions. But it could totally be done in the lab. All right, moving right along here, ionic compounds are blank conductors in their solid form. You'll notice we have another blank after this, which compares it to their liquid form. So first, your ionic compounds are poor conductors in their solid form. They are poor conductors. They are not very good conductors of heat and electricity in their solid form. So the reason why electrical charge, so electricity is just a stream of electrons. So electrons and heat, for that matter, can't conduct very well in ionic compounds because of their rigid crystal lattice. So the crystal lattice is so rigid, it has these positive and negative pockets. So any negatively charged electron or stream of electrons is going to be pulled towards